If you have a timing critical path that includes a counter, you can try to re-encode the counter to one of these other styles. While synthesis tools build binary counters by default, these other counters have advantages. The binary counter is slow but provides a familiar count sequence. It also uses the least amount of registers. Also remember that a true binary counter is actually the least significant bit. It's the only bit that actually toggles with the clock rate. So even if it says you have not met the timing for a counter, in most situations you have met the timing needs. Since every bit after that, each bit only needs to perform at half the rate of the previous bit. In other words, if you have a 4-bit counter, bit 0, the least significant bit, runs at the clock rate, but bit 1, or the second least significant bit, runs at half that clock rate. A one-hot encounter is very fast and uses more registers than binary encoding, but in an FPGA implementation, there may not be anything wrong with that. There are many registers available, but it will depend on your design. By using one-hot, you have a simple decode to perform by only looking at one register, so the decode logic is obviously reduced, and this allows it to run faster. Johnson is kind of a mix between binary and one-hot. It's a ring-type counter, fast and uses fewer registers than one-hot. It also reduces the decode logic necessary. The LFSR is very fast, using a pseudo-random sequence. It uses fewer registers than one-hot as well, almost as few as binary encoding. In general, designers don't usually design with these counter types, and for a less experienced user, I would suggest that you build it binary. Then, if you end up having a timing critical path with a counter, as part of that path, consider trying one of these types of counters. As an FYI, another common problem designers have is using the appropriate timing constraints. In the Designing for Performance course, we discussed the use of false paths and multi-cycle path constraints and their use with binary counters and other counters. Another good design practice is to use case statements when you are building decode logic. This simplifies the logic and consequently reduces the complexity in the number of inputs used to build the decode. This saves LUTs and reduces the number of levels of logic, which improves the speed through decoders. So in this example, a nested if was used to check for conditions. You can literally read through this to get an idea of why it's slow. If this, else if this, do this. Otherwise, if this, do this. Otherwise. So to help large decoders, we recommend using a case statement. So let's go to the next slide and we'll look at an example. When we rebuild this decoder, you see that we assign default values and then check for a range of conditions. This narrows the testing and reduces the complexity of the logic, thus making it faster and smaller. So if you find you have a timing critical path through some decode logic, consider rewriting it to use a case statement. We've already discussed pipelining in some detail in previous RELs. So you should remember that pipelining adds registers but shortens the delay between registers. The caveats to pipelining include using more registers and creating latency. Latency is usually resolved by balancing pipelines, but some applications cannot tolerate extra latency, so it will be up to you to decide if your application can handle it. In case you have built FPGAs before, keep in mind that Vertex 5 with its 6-input LUT will not need as much pipelining as other architectures that have a 4-input LUT. So pipelining is hopefully becoming less necessary. Now once you have pipelined, keep in mind that your synthesis tool's retiming option may help you more now. Recall that retiming moves registers forward and backward in a data path to improve the speed. We discussed synthesis options in the Designing for Performance course. It is also recommended that you register all inputs and outputs of your design. You may already know this. It's pretty common knowledge, but this is the most reliable and fastest way to clock data into or out of an FPGA. These delays are also fixed, so no programmable interconnect is associated with the IOB resources. What you see in this case is what you get. You should also use the DCM and PLL resources appropriately. We covered this in an earlier REL, but it is important to remember. Other ideas to increase your design speed include targeting the DSP slice for multipliers and other large arithmetic operations. This can be easily done by creating the appropriate core and then instantiating that core into your design. You might want to consider registering selector expressions, inputs and outputs for muxes and decoders. This becomes most important for large muxes and decoders since they will most likely generate the most logic levels. But this becomes most important when you consider that these types of components are purely combinatorial. So if you don't register them, you will probably need to insert a pipeline stage later, since the extra logic will create a timing critical path. So go ahead and get used to registering the inputs and outputs of your purely combinatorial logic now. Also, if you have multiple stages to an adder, register each stage, or port the component to the DSP slice. You should always register the input and outputs of your top-level design since this will register the I/O to your design. This will shorten your I/O time and improve your chip-to-chip delays. It is also a good idea to register the outputs of each of your subblocks since this will shorten the component-to-component delays in your design. This also helps remind you to evaluate the delay times between your hierarchical blocks and pipeline those paths if necessary. This is also important if you are not going to be using any incremental design methodologies, since these paths will not be as sensitive to placement. So this is a good idea to build your design this way no matter what. This diagram describes the relationship between system speed and logic levels, or as this diagram says, the number of LUTs between registers. While we have already spoken about what a logic level is, you can see from this chart that as you increase the number of logic levels, the need for pipelining becomes more and more critical. This diagram was made for one of the older Vertex 2 devices, but the principle still applies to Vertex 5 and all FPGAs. However, since Vertex 5 has a 6-input LUT, this correlation will not be quite as dramatic. I would probably say that for Vertex 4 and older designs, which are all 4-input LUT architectures, a designer should try to maintain 4 or fewer logic levels. Likewise, Vertex 5 designs should be held to fewer than 3 logic levels. This is not so much of a device issue, but what most customers need for their system speed needs to be met. By focusing on this common FPGA performance issue sooner, we are hoping customers will be able to build some pipelines in their applications sooner rather than later, and thus be happier with the result earlier in their design cycle. This diagram also illustrates that the more you pipeline your design, the less susceptible your design is going to be sensitive to a bad parse solution that hurts your design's performance. In the end, performance is defined by each customer. So if you need less speed, pipelining will be less necessary, but that is going to be your call.